23rd. And the mole concept is really important for today. So when you look at how we count things, we might say 1 dozen things is 12 things, right? So if I say a dozen kids, I mean 12 kids. If I say a dozen donuts, I mean 12 donuts. If I say I have 15 dozen of something, I can use this as a conversion factor, right? I can cancel out dozen if I write 1 dozen, and I can find out how many things. So 15 times 12, there's no help for that. Anyone? 150 plus 30, 180? I think. Not in my head.
That's correct.
Okay. Like another math trick. I made that 10. 15 times 10 is 150. 15 times 2 is 30. 150 plus 30 is 180. So, 180 things. Just like we use the word dozen to mean 12 things, and we can use it as a conversion factor to cancel out units even. 1 mole means 6.02 times 10 to the 23rd thing. Right? That number is so big it's beyond your imagination and mine. Like, way beyond what we can imagine a number of things. So, this is called Avogadro's number. Amado, I don't speak Italian, but he was an Italian scientist. Amado Avogadro found this number experimentally, which is unbelievable. Like, this is not like crunching a bunch of mathematical equations and getting this number. This was lab discovered number. Today, they've got Avogadro's number out to 8 decimal places, and the best, most precise way to calculate it is by X-ray crystallography, which is awesome lab technique using a big machine. Just stick your sample in and it gives you a bunch of data. Super fun. But, you know, they have confirmed what he did in his primitive little chemistry lab a couple hundred years ago. So that's really cool. What it means that 1 mole is just like a dozen, except 6.02 times 10 to the 23rd things. So picture that many things. Okay, so let's say if I had a mole of unpopped popcorn kernels, would it fill the room? The gym? Cover the state of Maryland? Anyone want to take a guess? It will cover the entire continental United States to 9 miles deep. A mole is a big number. Okay, how about a mole of soda cans?
At least half the world.
It will cover the entire world, the surface of the earth to 200 miles deep. Right. A mole is a big number.
Recycling.
Yeah, for real. Like, if we keep drinking soda, it's right, the whole earth is, no. Not crushed ones, just, you know, full-size soda cans. If we had a computer that could count to 10 million a second, right? Think, if it could count to 10 million every second, it would still take it 2 billion years to count to a mole. This is a big number. Like, really, really a big, big number. So, I'm sure when he got this result, he was like...
He probably looked it over more than once.
I'm guessing, like, call a friend. No phones back then.
What's the decimal?
Send my royal lesson.
Like if it's 10 to the 23, so that's like there's 23
Zeros, yeah. So it is like 6 gajillion. I don't even know. Like bajillion. Like, it's a big, big number. It's not a tiny decimal number. It's a huge, like, bigger than the national debt. Maybe the only thing.
It's a good thing.
It's a big number. So a mole is big, but if I want to measure out a mole of something, how would I go about doing it? If I wanted to hold a mole of aluminum in my hand, how would I do it?
So you find the atomic mass and then like the aluminum.
What's the atomic mass of aluminum? You might want a periodic table. So the atomic mass of aluminum is 27, this one says 26.98, but you guys only get to the tenths of 27.0. So that means that one atom of aluminum has a mass of 27.0 atomic mass units. But it also means what?
That's like that's
That's how many
that
grams are
amount.
in there.
Ah, so one atom of aluminum is 27.0 AMU, but one mole of aluminum is 27.0 grams. That's the power of the mole. So how hard is it to get a mole of aluminum? Not very. Alright, I'm on ounces because Matthew tampered with my scale. Grams. There. Squish. Alright, that's gonna take a while. 27, what's half of 27? I'm doing the math in my head.
13.5.
13.5, that might be a more reasonable amount. I don't want to waste the whole roll, right? Half a mole of aluminum coming up. And it's a little over.
Is this qualitative?
Yes, this is a qualitative measurement. I'm 5/10 of a gram, 5/100 of a gram over. I gained weight when I ripped that off. Your current problem. Half a mole of aluminum right here. Hold a half a mole in your hand. Think how big a number that is. How many atoms? Right, even half of this. If they were popcorn kernels, we'd be dead.
It'd be even worse if you heat the world up.
Yeah, it'd be awesome.
It would be saltless.
Well, we could get a couple moles of salt and be all set. So what about water? How would I measure out a mole of water?
Well, wouldn't you get the total AMU mass, and then that would be equivalent to 1 mole?
Yes, so what is the molar mass of water?
Well, it's 1.0.1 times 2 is 2.02 plus 16.0, is that correct?
Mhm.
And then we would drop the hundreds too, because it's, then we have 8.0 AMU, which is the total mass, and then that 1 mole of that would be equivalent to 20, would be equivalent to 18.0 grams.
Okay.
Correct.
So I could measure on the scale 18.0 grams of water, and that would be a mole of water. What else do we know about water that makes this a lot easier?
It's the same. It's like finding it's the same with the tiny molecules, molar molecules. Like
Yes, but that won't help me measure the water. Something else.
I don't know.
What's the density of water?
Mass times volume.
Anyone remember the actual density of water?
Oh, it wasn't 4.184?
No, that's the specific heat of water. So this is, so the density of water is so easy. It's 1.00 grams per milliliter. So that means that 1 milliliter of water weighs 1 gram. So 18 grams of water would weigh, or would have a volume of 18 milliliters. So, 1 mole of water coming up. And that's 25, that's how you're mole. Just a little under. Passing around 1 mole, 18 grams of water, 18 milliliters of water, since the density is so easy. 1 mole of water. So, just think, in that mole of water, 6.02 times 10 to the 23rd molecules. Like, staggering. That tiny little, not even a mouthful of water, has that many molecules. So you can imagine that a molecule is really small and an atom is really, really small. Yes? Maybe we can't imagine. I don't know if we can. So here's what I want to do. Before we do the lab, just to make sure we really cover the test requirements, let's look at maybe a couple of practice problems. So first, review question number 10 is the only one I'm going to talk about, and that very quickly. Review question 10 says, why must a chemical reaction be balanced before it can be used in stoichiometry? Well, stoichiometry is just the comparing of things, converting grams to moles, using balanced equations to figure out how much of something is in a reaction. So when you look at a balanced equation, this is the right one, like the formation of water, and then my balance here, we talked about how that meant 2 molecules of hydrogen plus 1 molecule of oxygen makes 2 molecules of water. What it also means is 2 moles of hydrogen plus 1 mole of oxygen gives you 2 moles of water. So the equation has to be balanced because that's the only time that you can use these coefficients. This one is a 1, it's just not always written in there, to compare moles to moles. You can say, if I have produced 2 moles of water, I've used 2 moles of hydrogen. If
How
I've
does
used
2 plus 1 equal 2? I didn't get this in the book.
2 plus 1?
And you have two moles of hydrogen, 1 mole of oxygen makes 2 moles of water.
Because their atomic
Different
mass
weights,
is also
okay.
added.
Right. I mean, when you combine here, you can see you've got 4 hydrogens, 2 oxygens, 4 hydrogens, and 2 oxygens. But not only does this mean atoms, it means moles, which we can't count or measure atoms easily. We can do it with moles because the periodic table gives us a way. It gives us the ability to say, I can measure out grams, right? 2 moles of hydrogen would have a mass of what?
2 grams.
Right. So, well, actually 1 mole of hydrogen would have that mass because it's homonuclear diatomic in its elemental form. So 2 moles of it would be,
4.0.4.
right. So 2 moles of hydrogen gas, I would just take my little tank and pump in 4.04 grams of hydrogen gas, and I'd know I had just used 2 moles of it. So it makes it easy in the lab to figure out if I need 2 moles, I can just convert to grams, measure it out, and there it is. Even with gases, if you have a nice tank and a really accurate scale, you're all good. So, look at practice problems. Let's do maybe 8, 9, and 10, I think. Practice problems. Okay, I'm going to start with Brittany. So practice problem number 8, Brittany, says, what is the mass of a CuCl2 sample? So, first off, let's look at CuCl2. Ionic or covalent?
Covalent.
Copper,
Oh wait, never mind. Ionic.
ionic.
Except, wait a minute. I want to find my.
So copper is right here on the periodic table. It's a metal. Chlorine over here, of course, a non-metal. So that's ionic. And ionic compounds don't use those prefixes. So what would this be called?
It would be called. What was the second one? Chlorine.
Chlorine.
Is it copper chloride?
Copper chloride. Perfect. So what is the mass of a copper chloride sample if it contains 0.172 moles of the compound? So the way I start a problem is I always just write what it says. Now, very important, you always want to write the chemical name in also, because we're going to start canceling units, but not just units. You can only cancel moles of copper chloride with moles of copper chloride. You can't cancel with moles of copper or moles of water or something else. So it's very important to keep your chemical names in and have them in your answer sheet. So that's what we know. And it wants to know how many grams? Yeah, the mass. So it wants to know in grams. It doesn't say kilograms, so you're fine with grams. So how do I do that? How do I convert from moles to grams?
I want to find the atomic masses of copper and chlorine.
Right, so copper is right in the middle, copper.
C3.5.
And chlorine,
35.5.
71, because 35.5 times 2. And so total is, so one copper chloride, I hate to say molecule because it's ionic, would have a mass of 134.5 AMU, but what else does that tell us?
One mole.
Okay, so 1 mole of copper chloride is 134.5,
And
well,
grams of-
one molecule is AMU, 1 mole is
okay, good.
grams. So here's your conversion factor. You got it on the periodic table by adding up 1 copper and 2 chlorines. So then you want to look at that conversion factor. Always keep the number with the grams when you do this. So if you have to flip over your conversion factor to cancel your units, which you don't in this case, because you want moles to cancel moles, you want grams in the numerator, because that's what the answer should be in. But if you have to flip it over, keep the number with the gram unit. All right, so mole of CuCl2 can cancel mole of CuCl2.
And I have a multiply list.
And what'd you get?
I can't find mine. 23.13.
And you have 3 here, 4 here, so you keep 3.
134.
What's your unit?
Wait, is it there?
And make sure you put your chemical names. So, 0.172 moles of copper chloride has a mass of 23.1 grams.